Passive two-phase immersion cooling, as an alternative to forced air or direct water cooling, offers many advantages related to power density, energy efficiency, and simplicity. Since these advantages must be weighed against the cost of the working fluid used to fill and operate the system, it is important to understand mechanisms of fluid loss, some of which are not intuitive. First, we must visualize the circulation of the fluid. In this system, we can see the container divided into three sections: the liquid in the bottom, the vapor layer above it, and the air above the vapor, called the headspace. In this system, the heaters take the place of the CPUs, and the condenser plays its normal role. This simulation shows the density of vapor in the air above the liquid. We see that as the temperature rises, more vapor is present in the air. Once the processor heats and the fluid begins to boil, the vapor density greatly increases and a layer of vapor begins to develop. As the vapor layer rises, it pushes the air above it out of the container until the vapor overflows. All of the fluid will boil out quickly, so we insert a condenser. The vapor will rise into the condenser, then condense and drop back into the tank. This stops the vapor layer from rising further. Here, we can see the top of the vapor layer as a line of condensation along the side of the container. The vapor layer is composed only of the vapor from the fluid, while the headspace above it has both air from the atmosphere as well as fluid vapor. The obvious solution might be to put a lid on the container. However, as the vapor layer rises, air in the headspace will be compressed, and pressure inside the system will grow rapidly. This increase in pressure can cause leaks and/or serious damage to your container. For safety, this air must be released during operation, especially on startup. This ventilation results in a small amount of fluid loss. Unfortunately, even after the vapor layer stops rising, there is still the possibility of fluid loss. When the system is in operation, the power delivered by the electronics is not constant. As it fluctuates, the vapor level rises and falls. When power increases, vapor from the headspace is pushed out. When the power decreases, air is pulled in. This motion is seen in the inflation and deflation of the bellows as shown. Without proper mitigation techniques, this causes small amounts of fluid to be lost, which, over time, can result in significant fluid loss. We have explored three techniques for fluid loss mitigation: cold traps, bellows, and check valves. When using any of these techniques, it is important to have an understanding of the benefits and the drawbacks of each. The first technique is to install a cold trap, essentially adding a second condenser. The cold trap cools the outgoing air to room temperature or 0 degrees Celsius, and effectively further lowers the vapor density, leading to less fluid escaping. With this method, we protect about 0.03 to 0.13% of the initial fluid volume to be lost on startup. Another way to mitigate fluid loss is to use bellows. Although this method is not as spatially accommodating, no fluid is lost using this method. A bellows is an inflatable bag which contains the tank's excess air while maintaining the system's pressure. As the fluid begins boiling, the air, which usually is pushed out by the rising vapor level, is instead pushed into the bellows, not allowing the vapor to escape, so no fluid is lost. The main issue with this technique is that the bellows must be anywhere from 1 to 2 times the tank volume. The last technique is to use check valves. These valves allow pressure during startup and shutdown to be vented, while containing smaller pressure changes, such as those during power fluctuations. This system uses a simple ball check. The ball is lifted by the pressure inside the container and will spin as the air is released around it, causing losses on startup of about 0.1 to 0.5 of the initial fluid volume. When the pressure stabilizes, the ball settles, sealing the container. This means that no more fluid is lost during operation. The advantage of these valves is that they are very small when compared to the bellows and only allow for fluid loss on startup. While expected losses vary based on individual systems, predictions outline losses on startup to be between 0.1 to 0.5% of the fluid volume with just an open container. This is reduced to 0.03 to 0.13% with the use of a cold trap at 0 degrees Celsius. With the use of a bellows, there is no fluid loss. Power fluctuation results in much smaller losses. 0.02 to 0.1% without any mitigation is reduced to 0.006 to 0.02% with a cold trap at 0 degrees Celsius. Check valves will mitigate losses due to power fluctuations, but would be the same as an open container during startup. We hope that we've been able to bring to light some of the nuances involved in immersion cooling. When done properly, there are numerous benefits over traditional methods of cooling. It is important to have as much information as possible before investing in immersion cooling, and you should always consult an expert before doing so.